Recording is rolling. It is Friday, October 18th. Last time I saw some of you guys yesterday. We did a story at the Media Center about Fermi paradox, but the day before that, you guys were doing Centripetal Force Lab. So we're going to put all the graphs together. Remember, you might have a couple of the graphs done because you could do a couple maybe, but not all of them because I had you guys split up into different experimental teams. We're at the end of quarter one, so yeah, if you guys got anything turned in, make sure it turned in. About the last day I can get stuff in the grade book. Your guys' puzzle, I know I gave you guys some puzzles a week or two back. Well, I've got different pages for different classes, but I don't have a due date for those yet. Now, for AP, there is a progress check, AP Classroom. So I have to bump that due date back another week because hurricanes and testing and whatnot. So let's have that due 10 days from now. I think it's going to be a good day. Now, guys, this AP Progress Check Unit 2, a lot of the puzzles you can solve already, but not all of them because we haven't covered all the content yet. I still need to talk to you guys about universal gravitation and orbits, which we haven't talked about yet. We have to finish this Centripetal Force Lab first, otherwise nothing else is going to make sense. Okay, so here, guys, this weekend, if you've got some spare time, like, oh man, I really wish I had some physics homework. Well, here you go. Go on AP Classroom, check out this unit 2 progress check, and you can probably do most of the puzzles, right? And then we'll eventually go over those in class. All right, so ASVAB is coming up in a few days. Guys, ASVAB, most of you guys are taking the ASVAB. So you guys remember I told you guys, where's there an Excel page that tells you where you're testing if you're testing? Where can you find that? Google Classroom, that's on Google Classroom. Now, I did go amend that this morning because I have a new page that says where you're relocated if you're not taking it. There are probably 5 or 10 of you guys in here who are not taking it. So here's my relocations. So period 1, okay, well, you guys can see my first 4 classes, and you guys can see where you're going to go. That is also posted to Google Classroom, so you can know your relocation data if you're not taking it. Right, so everybody know where to find all that information. It's all in Google Classroom. It's all there. Right? All right. All right, so let's do Centripetal Force. Okay, so here, note for if you're watching this video at home, I still have a little bit messed up projector. I'm getting that fixed, so it's gonna be fixed soon, but I might have to zoom in on parts. So if I have like this paper off center and I'm kind of zoomed in on it, that would be why, just for so everybody in the class can see what's going on. All right, so I had you guys split up into 3 different experimental groups. You guys filled out this table, but remember there were 4 different variables that you guys were filling. Let me get a picture for reference. Right, so you guys know what I'm talking about. Right, there were, and I've got part of this covered up, the equations that we're going to derive in class. Right, so you guys had this PVC pipe, string, couple Play-Doh canisters. Right, so the mass of the one swinging, that was the variable. Right, how much force would it take to keep this in the circular pattern? Well, that would be the weight of the one that's hanging. That could be a variable. The radius of the circle could be a variable. And the speed, how about V, that for maybe a tangential velocity, that could be a variable. Right, so those are 4 variables. So what you guys did was kept 2 of those controlled, 1 independent, and then everybody treated the speed as dependent. And then now we're going to put those 3 different experiments together. Okay. So now let's start. So at the top left here, what do we got? We got this says speed versus the weight hanging for a constant mass and a constant radius. That would be constant mass and constant radius. That looks like the diamonds, I think. Guys, who had the diamonds? Who had the diamonds? Okay, all right, so you guys back there are diamonds. All right, so let's see. So we can make this one. Yeah. So I'm gonna label this here. Guys, go ahead just for a good practice and also label this the same way I'm labeling it. We zoom out as far as I'm able to just for the projector. Okay. We got a couple axes. I'm gonna make a full-size graph here. It says V versus R. V versus R. So speed versus radius. Right? Guys, that means which variable goes on the vertical axis? Speed. And that's going to be in, hey, but you guys had you were measuring in meters. So let's go ahead and call this meters per second. Okay, I had you guys measure in meters. Right? And then radius is down here, and that was in meters. Okay. All right, so I'm going to get some data from Hans. Hans, what was your largest radius? Oh, wait, did I? Oh, I'm so sorry. That's not diamonds. Never mind. I picked the wrong one. It was V. Oh, V versus. Oh, whoops, I read the title wrong. V versus weight hanging. Oops. Sorry, you're right. So this is force. Now, guys, when I say force, I'm talking about the tension force, which is equal to the weight hanging. So yeah, sorry, I messed this up. That's not the first one. All right, again, the weight, which is equal to the tension force, which represents the centripetal force. Okay, and this is going to be in, guys, what unit could you measure force in?
Newtons.
Yeah, you can measure newtons. Now, I think on your paper, I had you guys do millinewtons, right? So maybe you had like 1,000 millinewtons or something like that. I'll go ahead and do millinewtons down here, okay? Because you're working with like little gram masses and that sort of thing. Okay, guys, milli is a factor of a what? 1/1,000. So 1,000 millinewtons would equal 1 Newton. Is that right? Okay. All right. So sorry, Hans, I asked you the wrong question. What was your largest hanging weight? That's what I should have asked. Okay, yeah, go ahead. Okay, so I should change this to just plain newtons. Is that right? Yeah, as long as it's consistent all the way across, that'll be right. We're just looking for a proportional relationship. So you had 11.6. So I'm going to scale this. How about 3, 6, 9, 12? That should do it. 0, 3, 6, 9, 12. Dash, 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 dash. Right. Guys, did everybody right now? Let me make sure everybody's on the same page. Okay. Everybody labeled a variable and a unit on this axis, right? Because last couple labs, a lot of students are missing that variable unit. Because whenever you look at a graph that's like professionally published, it always tells you what's on the axis. It's not just like a random axis, like, oh, random 3, what 3 what? Right? Oh, 3 newtons. Okay, all right, now I know what that means. Okay. And guys, make sure you start your axis at 0 and then scale it accordingly. Every once in a while you see one, but okay, in this class, they're always going to start from 0. Okay, start from 0 and just scale it linearly, just like I did. Okay, you guys see that? Okay. All right. So, Hans, also, what was your fastest speed? 2.55 meters per second. Okay, so I'll go 1, 2, 3. So 0, 1, 2, 3. Did you guys also label the vertical axis speed? And you put the unit meters per second. So again, whoever's reading your paper knows what they're looking at. And start at 0 and scale it linearly, just like I did. I scale up to 3. So all the data should fit in that space right there. You guys all got that? All right, let's get some coordinates. So Hans, what's one of your coordinates?
For the 5.6 newtons meters, it's 1.73.
5.6, 1.73. All right, that's right about there. I'll label that 5.6, 1.73. All right, it's newtons and meters per second. All right.
6.6 newtons plus 1.82.
6.6, 1.82. All right, it's about right there. 6.6, 1.82. Oh, the units embedded. Yeah.
7.6 was 2.03.
7.6, 2.03. 7.6, 2.03. Yeah.
8.6 was
8.6 is 2.2. 8.6, 2.2.
9.6 was
9.6, 2.23. 9.6, 2.23.
and 10.6 was 2.35.
10.6, 2.35. I asked.
11.6 was 2.55.
0.35. So you said 11.6 was what?
2.5.
2.55. Okay. All right. 11.6, 2.55. All right. Okay, so I think that's about where those go. F versus V versus. All right. Okay. So now we got to figure out. Yes, sorry, some of those labeled coordinates get in the way of the dots a little bit. Right. That might even be 100% exactly where they go, but it should be pretty close. Trying to get them pretty close where they go. Okay. Now we got to figure out what relationship is that. Let me dig through my old posters. I'm going to find. Aha! Here's the poster I'm looking for. Okay. Common graphical relationships. I think I told you guys a long time ago in this class. There's really only a handful of graphical relationships you'll see in the labs over and over in this class, and all of them from your lab are going to be somewhere on this page here. Okay. Which one do you think that is? Great. Let's throw a candidate for linear. And if it's not linear, which one it might possibly be? Maybe one of these. Okay, so I'm hearing nominations for linear or parabolic or root. It's probably one of those. And sometimes it's hard to distinguish those. So let's go back to this data. Right? Now, if you thought it was linear, if you thought, oh, those points might look like they line up in a straight line, then you could take a ruler, you could line them up in a straight line, and you go, line of best fit. And, oh, look, that has a huge y-intercept, doesn't it? Right? And then pause for a moment, think, okay, what would that mean to have a huge y-intercept? Well, that would mean at 0 hanging force. Okay, so if you took that bottom canister and just like cut it off, so you just have an empty string down there, there's like 0 weight hanging. Okay, that it would take some speed to keep the top mass in motion. Would that make any logical sense? I don't think so. And of course, you could go back and you could do the scientific version of that. You could actually try it out. That it wouldn't work. The top canister would just like fly off, wouldn't it? Right. So I don't think this is linear. I think this is more logically. And again, you could scientifically go back and grab the data for this. I think probably makes more sense that 0, 0 probably has to be a point. But the only way for 0, 0 to be a point is this has to bend. How? Yeah, it's probably more like a square root type curve. I think it's more like a square root. And guys, this showed up also with your car and incline lab, and this is going to show up on probably some future labs too, where if you get a bunch of data that's way out here on the tail, it might look linear at a glance. But if you go back and you grab data that's closer to the origin, it's actually going to bow down, and it's going to reveal more accurately what the graph actually is. Yeah, so this is probably a square root curve. So I'm going to make a guess. I'm going to guess that v is proportional to the not f, but the square root of f. Okay, so I got v proportional to the square root of f. Okay, maybe I'll put a question mark. Maybe I don't 100% know for sure. But how could I test that out? Right? Or if I did know that was true, how could I get the equation of this square root curve if it is a square root? Right? And either way, there's a particular process that AP wants you to do, and it's called what? Starts with an L. Linearization. Linearization. Got it. Yeah. Yeah. Right. So if I suspect that this is true, and we've done this before, there's 2 ways I could do this. I could graph v versus the square root of f. So instead of f down here, I could do the square root. I could square root this whole axis, right? And the points should line up in a straight line. Or alternatively, what we're going to do, just make this consistent for everybody's experiments. I could square both sides and say v squared, therefore, would be proportional to f. Wouldn't that also be true? Like if this is true, this has got to be true, right? You just square both sides. This proportion is kind of like an equal sign. So let's do that. And that's, I gave you guys a graph space. Where is it? I forgot to put this on the other side. Do you guys see the one on the top on the right side? It says v squared versus weight hanging. Right. That's the one we're about to do right now. Okay. You guys see that one? Top right. Okay. So let's do that. Let's do, and that's also why in the table I gave you guys the v squared column. Actually, everybody's going to need the v squared at the end. Just a little hint. That's going to work out. So let's do not the speed versus the hanging weight force, okay, but the speed squared. Okay. And so vertical axis, label that v squared. That's going to be in. Well, I know speed is in meters per second, so we're going to square that whole thing. Okay. You guys go ahead and label that vertical axis like that. Let's do that. Okay. And that's as a function of the weight hanging, which is a force, which is, well, it was in newtons before, so I'll keep that in newtons. That could be force in newtons. Okay. Remember, which is also equal to the tension on the string. That's why the lab setup is the way it is. Okay. Well, actually, I know that axis is going to be the same. I'm going to label it 3, 6, 9, 12. So 0, 3, 6, 9, 12. Force in newtons. Everybody gets so far. Doing all right? Okay. But I got to square all these speeds. Now, the fastest speed before was about 2.55 meters per second. What do I get if I square that? It's like 6.5. Now, that'd be meters squared per second squared, kind of an abstract unit. Okay. Maybe I'll scale this up to 7. 1, 2, 3, 4, 5, 6, 7. So remember, start at 0. Right, and they go 1, 2, 3, 4, 5, 6, 7. Right. So if you have everything completely correct, then you have each axis label. There's a variable and a unit, variable unit for each axis. You have each axis scaled linearly starting from 0, just like that. Everybody has that? All right, let's get some coordinates on the board. All right, so Hans, what's one of your coordinates now?
5.6 newtons, it would be 3 meters.
All right, so 5.6, and then you said 3 meters per second square, or meters square per second square. So you got 5.6 newtons, and then 3 meters square per second square. All right, what's another coordinate? 3.2, 6.6, 3.29, 6.6 right about there. 6.6, 3.29. All right, what else you got? 7.6, 4.11, 7.6, 4.11. All right, next one. 8.6, 4.82. 8.6, 4.82. Okay.
9.6 was 5.
All right. 9.6 was 5. 9.6 and 5.
10.6 was 5.54.
10.6 is 5.54. Okay.
11.6 is 6.5.
11.6 was said 6.51. 6.51. 6, 6.51. All right. All right. Now, yeah, no, those points right there looks like line up pretty straight through the origin. So that, yeah, that's about, yeah, now that's a straight line through the origin. Okay. So, yeah, so now I can say b squared is proportional to f. You could even come up with an equation. You could say, but the catch is though that whatever equation you come up with for this line, which you could just get the equation of a straight line, right? Just find the slope rise over run and do like y equals mx, except it's b squared equals slope times f. Right? That equation only works for whatever radius that chain had and whatever the mass of the swinging bucket was. So if you change either one of those, then you have like a different line, maybe it'd be like steeper or shallower. Okay. But I know this for sure. I know b squared is proportional to f. I know that, right? Regardless of what experiment you had. All right. That's good so far. Good so far. All right. So far you've got here. I'm making a checklist here. You have this curve, which was some kind of square root looking curve, probably. Okay. And you guys have this. Well, I'll call it a curve because it's the math term for it, but it's really a straight line. So linear relationship. You have that one. You have that one. Okay. All right. Let's move on to let's say B versus R. No, B versus R. So I think this would be the clubs. Yeah. All right. So guys, who had clubs? Who had clubs? Wants to share their data? Clubs. Yeah. Okay. How about? Okay. Let's pick another clubs then. How about All right. How about this team over here? Did you guys have? Do you guys have clubs? Yeah. Okay. I'm gonna get some data from you guys. Okay. So, let's see, Joseph, what was your largest radius that you used?
The largest radius we had was 1.3 continuous.
All right, so like 1.33 meters?
Yep.
All right, so let's put on the horizontal axis, let's do your radius in meters. Okay, let's go, let's see, about 0.5.
I apologize, I misspoke. There was 0.75.
Oh, 0.75?
Yeah, we had a calculated rate.
Okay. So 0, 0.25, 0.50, 0.75. I think that should work for the radius.
Yes.
Right. And then what was your fastest speed?
Fastest speed, so our fastest velocity would be 6.69.
All right, so I'll put speed and meters per second. All right, let's go.
No, wait.
Huh?
Sorry, it was 9.4.
9.4. All right. All right, so let's go about 5, 0, 5, 10. Maybe do that 0, 5, 10. Then okay, so that should hold all the data right there. Okay. So if you guys meant to catch up, you guys have the vertical axis labeled V in meters per second. You guys have the horizontal axis labeled radius in meters. You threw down some numbers, have it start at 0, 0, everything scaled. I have all that. All right. All right, let me get this recharge on. I think yeah, I got a new amp in here. I think this one's working a little better so far. All right, so let's get some numbers. What's one of your coordinates?
The smallest one we have is a radius of 0.25 and a velocity of 3.55.
Let's see, 3.55. All right, so this is 0.25, 3.55. This is meters, and this is meters per second. All right, what else you got?
The next one is a radius of 0.5 with a velocity of 6.69.
6.69. Okay. So 0.50, 6.69 meters per second. Okay, and
Our last one is a 0.75 radius with a 9.4 velocity.
9.4. Okay. 0.75, 9.4 meters per second. All right. So normally I ask you guys what relationship does that look like? Now, me looking at it, I think it looks kind of linear. With just a few data points, sometimes it's kind of hard to tell. But I can tell you what the textbook answer is, and what we're just going to run with and move forward with is that normally, let me double check. This should B versus R. Yeah, normally this should also work out like a square root curve. Okay, so we're just gonna assume like if you have lots more dots, that would be the case, and we're going to go through the same process as we did with the last experiment and see what does that look like. So let's say we had lots of data and got to the conclusion like, oh, that looks like a square root type curve. Okay. Then the next step would be to, or again, if you assume, see, b squared is proportional to r, or say if b is proportional to the square root of r, it's the same idea. Okay. I could either graph v versus the square root of r, that should linearize, or I could square both sides, like before, get v squared versus r. That's what we're going to do. We're going to eventually relate everything to v squared so that we have 3 experiments that are consistent with that axis v squared. Okay. So let's do v squared and meters per second being squared, okay, as a function of r and meters. So scale this, doink, 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 0, 0.25, 0.50, 0.75. Okay. Okay, and then vertical axis, let's probably go up to about 100, right? So let's go about, maybe I could do a centimeter at a time. Can I do 10 centimeters here? Yeah, that would work. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 0, 50, 100. Okay. So let's get these points. So if it was, say, 3.55, if I square that, I get 12.6 about. Okay. So 0.25, 12.6, that's right about here. 0.25, 12.6. Okay. If I square 6.69, getting 44.8. So 0.5, 44.8. And if I square the 9.4 meters per second, 9.4 squared, getting 88.4. So 0.75, 88.4. Okay. Again, now on the paper, of course, it looks more like a parabola, but the textbook answer is that this should kind of linearize. So we're gonna run with that. Okay. So let's say we have that type relationship, something like that. All right, and that is I was gonna point it, but you guys probably figured out that's this graph over here, right? Sorry, b squared versus r. Yeah, there you go. B squared versus r.
Can you share the graph one more time?
Yeah. Why did I type it like that? Huh. Remember.
Is the second one 44 something?
44.8. Yeah. Yeah. All I did was I took the original 6.69 to square that. But yeah, 44.8. All right. So B versus R, again, by the textbook, ideally should be about a square root curve. Therefore, if you do B squared versus R, that should line up linear relationship. Okay. All right. So we got one more to nail down. That's the speed versus the mass swinging. Okay. So the last group was changing out the swinging mass right here. Right? So if you are making this heavier and heavier, how do you have to swing it? What exactly is that relationship going to be? Right. So V versus M. V versus M. Okay, I think that was the spades. So who has some good spades data? All right, all right. So Hector, gonna get some data from you. All right, what was, so we're gonna do V versus M. So let's put speed in meters per second on the vertical axis. Let's put M, or it's a swinging mass, so that's the one we're interested in. Okay, this could be in maybe grams. All right, so Hector, what was your largest mass that was swinging around? 81 grams. Ooh. All right, so let's go. Ooh, all right, pretty good. All right, so I'll do 20, 40, 60, 80. So 0, 20, 40, 60, 80. Okay. Okay. And then what was your fastest speed? 7.08. All right, so let's go 1, 2, 3, 4, 5, 6, 7. Okay. So 0, 1, 2, 3, 4, 5, 6, 7. All right, so a little bit more than that. That should work. All right, so what's one coordinate? All right, 11 grams was 7.08. It's right about there. So I got 11 grams, 7.08 meters per second. What's the next one?
1 gram is at 4.62.
4.62. Okay, so got 31 grams, 4.62 meters per second. Okay, next one.
41 gram, 4.58.
41, 4.58. Okay, it's right about there. 41, 4.58.
51 is at 4.39.
51, 4.39. Okay, so 51, 4.39.
At 61 is at 3.8.
3.83. Okay. 61, 3.83.
Then I think the next one's a little bit off, but 71 is 4.1.
All right, yeah, better than I take. 71, 4.1. It's more like up there. So this one is 71. You said 4.1? Okay, 4.1. Okay. All right.
Then we have one,
Yeah, go ahead.
81 is at 3.58.
3.58. Okay, so 81, 3.58. All right. Okay, you guys think there was definitely some kind of inverse relationship? There you go. So you guys know inverse relationship, you make one variable big, the other gets small, vice versa. Okay. Right. Yeah, so something with inverse. So we come with the equation. I think B is proportional to 1 over the mass somehow. And there might be more to that story. Maybe that's not all. You know, maybe there's something to do with square or square root, maybe. But I'm going to start with that. I'm going to invert one of those variables. Let's invert the mass. Let's do B versus 1 over the mass. Because that might linearize, or if it doesn't linearize, then it'll at least get us closer to a linear relationship. This is definitely some kind of invert. If I put a curve of best fit, I think it's going to be probably something about like that. Okay. So let's do V versus 1 over the mass. So you guys' paper so far, V versus mass did something kind of like this. Okay, we're going to do V versus 1 over the mass. So I'm going to put V, and I guess V would be the exact same as before. So let's do meters per second. And this could go up to 7. 1, 2, 3, 4, 5, 6, 7. Well, here, I'll throw in an 8 because there was a 7 point something. 0, 2, 4, 6, 8. Okay. Now 1 over mass. So now we're definitely in abstract territory. Whoops, didn't mean to do that. Okay. So 1 over the mass, which could be the units 1 over grams. Okay. What's that going to look like? The biggest value I can have comes from the smallest mass, right? 1 over 11 grams. Let's see, what is 1 over 11 grams? Let's see what that 1 over 11 grams is, like 0.09. Okay, so let's call that 0.1. Scale everything else accordingly. So how about this could be 0.1 of those, and then divvy that into 10 parts. Okay, so we're getting the reciprocal of the mass. 0.02, 0.04, 0.06, 0.08. Right. All right, so Hector, what's one coordinate on this graph?
For 0.1 is at 7.08.
So, oh yeah, of course, right. So 7.08 is right about there. Okay, so we got 0.101 over grams and 7.08 at the meters per second. All right, what's another coordinate?
I don't think we did our 1 over mass.
Okay. Here, let's see. See what we can do here. So, like 1 over 31 grams is 0.03. So 0. And that would be 4.62, 4.6. 2. So we got 0.03, 4.62. Let's see what else we got. 1 over 41 is 0.024, 4.58, 4.58, 0.024, 4.58. Right. What we got is here, I'm just gonna hit this last one. See if the last one is 1 over 81 is 0.012. That's 3.58. Wait, 12, 3.58, right about there. 0.012, 3.58. Okay. All right. Anyway, I know I skipped a few, but this will tell the story. Guys, does this look like it looks maybe this way, like this? Could that possibly be maybe a square root curve? You guys think? Okay. I think at this part of the story, the speed is proportional to not only 1 over the mass, but it's really the square root of that, maybe. I'm gonna put a little question mark. If that's true, then here's what we'll have to pick up on Monday. B squared would be proportional to 1 over the mass. So we still have one more graph to make. And then after we make this graph on Monday, we'll be able to put the whole story together, make one giant master equation for all the experiments. And then we'll guys definitely bring in your AP style write-up because we're gonna score that one too. All right, you guys have a good weekend. Remember, you can solve some puzzles on AP Classroom, and I'll see you guys on Monday.